begin today's lecture by quickly recalling what we were doing in the previous lecture. We defined what is a random variable. Random variable is a function from sample space to the real line, and we clarified the meaning of the set of all omega where x of omega is less than or equal to x as a subset of the sample space on which we assign probabilities. We described the random variable through functions, three functions: probability distribution function, probability density function, and probability mass function. A typical probability distribution function is shown here. This is a probability distribution function for a mixed random variable. A random variable can be discrete where the probability distribution proceeds through only jumps, and in continuous random variable it proceeds without any jumps, and in mixed random variable there can be stretches where it proceeds without any jumps, and as well we can have jumps as shown here. We define probability density function as a derivative of this distribution function. Probability mass function is defined for discrete random variables. We considered several random variables. Bernoulli random variable is the basic building block. Here we basically deal with random variables which take only two states. This 0 is called success and 1 is called failure, and we assign probability p and 1 minus p. So, a sample space here is discrete. In a binomial random variable we deal with n repeated Bernoulli trials and ask what is the probability of k successes in n trials, and we have shown this to be a function of this kind where k takes values from 0, 1, 2 up to n. So, here again the sample space is finite, discrete, and number of successes to first failure we call it a geometric random variable, number of trials to the first success, that is defined. Suppose kx is the number of trials for first success. If we get first success on the k trial, we have got failures on the first k minus 1 trial and success on the k trial. Here k runs from 1, 2 and it can go all the way up to infinity. So, here the sample space is countably infinite. We also talked about models for rare event, that is where we were at the end of the last lecture. Here we are looking for occurrence of isolated phenomena in time or space continuum. We cannot put an upper bound on the number of this isolated phenomena, but actual number of such occurrences is relatively small. Some of the examples are, for example, number of goals scored in a football match where we are looking at isolated phenomena in time continuum, or we look for defect in a yarn in one dimensional space, this is 1D space continuum, or a typographical errors in a manuscript, it is 2D continuum, or defects in a solid, it is 3D continuum, or stress at a point exceeding elastic limit during the lifetime of the structure. So, here we are looking for isolated phenomena in time continuum. In this class of problems, the underlying random variables, namely the number of isolated phenomena, is given by this particular function. Here a is a parameter and k takes values from 0, 1, 2 up to infinity. So, the sample space here is countably infinite. A is a parameter of the probability distribution function. We can verify that probability of x less than or equal to infinity, which should be the probability of sample space, is indeed equal to 1. This is how the probability distribution function for a Poisson random variable with parameter a equal to 5 looks like, and this is the associated probability density function expressed in terms of set of Dirac's delta function. So, this is a discrete random variable with countably infinite sample space, and it is going to be very useful in variety of context, and we will come across this random variable quite often in later discussions. Now, we can obtain the Poisson probability distribution function as a limit of the binomial probability distribution function. Here for a binomial probability distribution function, that is for a binomial random variable with parameters n and p, probability of k successes in n trials is given by this. Now, what we will do is we will make the number of trials to become very large and probability of success in any given trial going to 0, such that the product NP goes to a constant, and we will look at realizations of x for small values of k. So, we are essentially simulating the prescriptions for a rare event, namely the probability of success is small. There is actually no bound on number of successes, but in practice the what we are looking for is number of success to be quite small related to n. In such a case, the binomial distribution can be shown to become Poisson distribution. A simple proof for this can be constructed by manipulating the binomial distribution and imposing the limit that we are putting, that is n goes to infinity, p goes to 0, such that np goes to a constant. If we do that, indeed one can prove that the binomial distribution goes to a Poisson distribution. We will consider some numerical examples so that we understand what exactly is meant here. Let us consider a binomial distribution where we are conducting 1000 trials and probability of success in any single trial is 10 to the power of minus 3. So, if we faithfully follow the binomial model, n is 1000, p is 10 to the power of minus 3, and if I am seeking the probability of no successes in 1000 trials, this is a rare event by the way, this will be 1000 C0 10 to the power of minus 0, and this 1 minus p to the power of 1000, the number is 0.36769. Now, this particular choice of parameters n and p are suitable for application of Poisson limit simply because n is sufficiently large, p is sufficiently small, and np, which is parameter a, is 1 here, and k that I am looking for is 0, that is indeed quite small compared with 1000. So, this is a situation where one could think of applying Poisson model for the binomial distribution, and according to Poisson model, probability of x equal to 0 is exponential minus a to the power of 0 by 0 factorial, and this turns out to be 0.36787, which compares reasonably with the number that we get from the binomial distribution. We will consider another example. We will consider a binomial random variable with n equal to 3000 and probability of success is 10 to the power of minus 3. Now, the question I am asking is, what is the probability of number of successes are greater than 5? Here probability of x greater than 5 is nothing but 1 minus probability of x less than or equal to 5. So, you have to sum the probabilities of this is 1 minus k equal to 0 to 5, this I am summing from 0 to 5. So, this can be in principle can be evaluated, but you will see that you will have a few numerical difficulties in doing this, but we can now explore if Poisson's limit is appropriate for this situation. So, number of trials is 3000 and probability of success is 10 to the power of minus 3. So, n appears sufficiently large, p is sufficiently small. So, the limit np, the product np is 3, and the range of k that I am interested in is k less than or equal to 5, which is quite small compared with 3000. So, the application of Poisson's limit prima facie appears reasonable. So, if we evaluate this probability, we get a number 0.084, and you can compare this number by evaluating actually this expression. Now, I will consider another random variable the Gaussian random variable, also known as a normal random variable. We will see shortly that it helps us to model situations where uncertainties emerge out of a summation mechanism, where different sources of uncertainties contribute to the final uncertainty in a parameter of interest, and they all add up. I will make these statements more precise as we go along, but right now we can look at the probability density function of a Gaussian random variable. So, here there is an exponential function and the square of the state variable is here. There are two parameters, one is appearing here, that is m, and other is sigma, which also appears here. X takes values from minus infinity to plus infinity. So, here the sample space is the real line and there are two parameters m and sigma. So, m and sigma are the parameters, and m itself can take values from minus infinity to plus infinity, whereas this parameter sigma has to be non-negative. A Gaussian random variable is denoted by n m comma sigma. N is for this word normal and this is m comma sigma. A typical plot of a normal probability density function for m equal to 2 and sigma equal to 0.8 is shown here. This is a familiar bell like curve which is symmetric about this line. This line is nothing but m equal to 2. You can see that this function is symmetric about m, that is what it shows, and as x tends to infinity plus minus infinity, the function decays to 0, and area under this curve is going to be 1. We will see how to prove that shortly. More on this as we go along. Right now we will try to see get familiarized with this probability density function. A specific form of a normal random variable is when the parameter m is 0 and this parameter sigma is 1. This is the n 0 comma 1 normal random variable, and the probability density function is here and it is symmetric about this line. It is symmetric about this line, and the probability distribution function is a continuous curve which starts from 0 and goes to 1. The Gaussian random variable can also be obtained as a limit of binomial random variable. Here the limit that we consider is, again we take n to be large, that is number of trials in the binomial random variable to be large, and q is 1 minus p, and we demand that the product npq should be greater than or equal to far greater than 1, and k itself takes values in the neighborhood of np plus square root npq and np minus square root npq, and if these conditions are satisfied, we can show that the binomial distribution can be approximated by this Gaussian curve. So, you recall now we started with a Bernoulli trial and constructed a binomial random variable, and I am using binomial random variable to construct Poisson and Gaussian random variables. In that sense, a Bernoulli random variable is a building block for constructing various probability distribution functions. Let us consider an example where n is 1000, p is 0.5 and k is 500. npq is q is also 0.5 because it is 1 minus p. npq turns out to be 250 and square root of that is around 15. Now, np minus square root npq is 485 and np plus square root npq is around 515. So, according to the Gaussian limits for binomial distribution, if k lies, mind you, our we are interested in k of 500, we are interested in knowing what is x equal to 500. So, k is between 485 to 515. So, we are in a situation where the binomial distribution can be approximated by a Gaussian curve, and we are getting this number 0.1030. This can be compared by actually evaluating this. Now, from the Poisson model, we derive what is known as an exponential random variable. How do we construct that? We will show that an exponential model helps us to model the waiting times between number of occurrence of isolated phenomena in Poisson model. So, let us consider a time interval 0 to t. Time interval 0 to t, and consider a sub interval t1 to t2 within this interval. Suppose if we place randomly n points in 0 to t. Now, we define the success if that point lands here. If the point lands in this interval, we say that it is success. That is, point lies in subinterval t1 to t2. So, probability of success is t2 minus capital T, which is p, because we are placing the point randomly in 0 to t. So, it can land anywhere with the same probability. Probability of failure, where success is the point lies in t1 to t2, probability of failure is point lies outside t1 and t2, is 1 minus p. Now, if we place n number of points, and we now ask the question, what is the probability distribution function of number of points in t1 to t2 after we have finished placing n points in 0 to t. So, this follows binomial distribution, and probability of x equal to k is given by n c k p k 1 minus p to the power of n minus k. Now, we will consider the Poisson limit of this binomial distribution. We will allow the number of points to become large, and we will allow the time interval t2 to t1 to become small in such a way that their product goes to a constant a, n t2 minus t1 by capital T goes to a, that means np goes to a. In such a case, we know that the binomial distribution goes to the Poisson model. Now, we denote by n by t, we denote as lambda, and t2 minus t1 as a. With that notation, a becomes lambda ta. Therefore, probability of x equal to k is given by the Poisson model exponential minus lambda ta to the power of k divided by k factorial, where k runs from 0 to 1 to infinity. So, this is a Poisson model for random points occurring in time continuum 0 to capital T. Now, we define now another random variable t star, which is a time for the first arrival. Okay? You start from 0, what is the probability that t star is greater than some time t? If the first point is going to arrive after t star, there will be no points in 0 to t. Therefore, probability of no points in 0 to t is given by exponential minus lambda t, where k is 0 in the Poisson model. Now, therefore, the probability distribution function of t star is given by 1 minus this, which is 1 minus exponential minus lambda t, and the associated density function is the exponential function shown here. So, here I have shown in this plot the probability density function for some value of lambda, it is exponentially decaying function, area under this curve is 1, and the associated probability distribution function is this monotone non decreasing function, which starts with from 0 and goes to 1 as this state variable goes to infinity. This t star can be used to model lifetime of a structure. So, in the definition of Poisson event, if we define the event to be for example, a stress at a point in the structure exceeding elastic limit, and that if we all agree that it is the definition of failure, then the time that we need to wait till that happens in a way is the lifetime of the structure. So, lifetime of the structure can be modeled as exponential random variables if the occurrence of the failure events follow Poisson distribution. We came across a similar random variable when we talked about discrete random variable, namely the geometric random variable. Geometric random variable was the number of trials for the first success. So, the exponential random variable can be thought of as a generalization of the geometric random variable for the continuous case. This exponential distribution has an interesting property that can be clarified here by considering the probability of T star less than or equal to T conditioned on the fact that up to T naught there was no event. Okay. So, that is by definition of conditional probability, it is T star less than or equal to T intersection T star greater than or equal to T naught and divided by probability of T greater than T naught. Now, if we use the exponential model for this and follow through the arguments here, you can show that the probability distribution of T star given that there was no event till T naught is given by this exponential distribution. Here T runs from T naught to infinity. That means it is continues to be an exponential distribution except that it has now shifted to T naught. In words, if you want to express what this actually is telling us, what it means is failure to observe an event up to time T naught does not alter one's prediction of the length of the time from T naught before an event will occur. The future is not influenced by the past, that is the message. So, this is also known as memoryless property. Now, we come to a new topic, namely transformation of random variables. To clarify what exactly is the problem here, we can consider a simple example of a cantilever beam carrying a tip load P. The cross section of the beam is rectangular where d is the depth and b is the breadth. L is the length, E is the Young's modulus, I is the moment of inertia, area moment of inertia. Now, we know that the tip deflection here is given by PL cube by 3EI. Now, if P, L, B, D are all random variables, then it automatically follows that delta is also a random variable. So, we will typically be interested in knowing if P and E are random variables and if we know their probability distribution functions, what can we say about probability distribution of delta? This is a problem that we have to answer in structural engineering. The inputs to a system, if this is uncertain, the output will also be uncertain. So, these input variables pass through our system through the physical laws that governs the system and produce uncertainty in the output. So, given the probability distribution of these uncertainties in the input and the definition of this system, the output is a random variable and what is the probability distribution of that output is a question. So, this is essentially a problem in transformation of random variables. So, let us make it more specific. Let x be a random variable. We will define a function y is equal to gx here. The question is, given the probability density function of x, what is the probability distribution function of y? And of course, the function g of x is also specified. To make the meaning of this problem clear, what we do is we plot g of x versus x here. Okay, this is x, this is g of x and this function is my g of x. And I will plot the given probability density function of x below this. Okay, say let this be the probability density function. and this is the unknown probability density function of y which we need to determine. Now, I consider the question, what is the probability that y lies between y and y plus dy? This is the question that I am asking, that is given by py of y into dy. Py of y is still unknown. So, if y lies between y and y plus dy, where all x can lie? So, to see that we draw these lines here. So, it intersects g of x at 3 places, this line from y, it intersects here, intersects here, intersects here. So, if y lies between y to y plus dy, x can lie here, x1 minus dx1 to x1, x2 to x2 plus dx1, or x3 minus dx3 to x3. So, whenever x lies in these shaded regions, y will lie in this shaded region, and these 3 events are mutually exclusive. So, this probability py of y dy is nothing but the sum of these probabilities. This is a probability density function. Therefore, the probability that x lies in this shaded region is given by probability density function evaluated at x1 into dx1, right. So, that is the first term, and px of x2 into dx2 plus px of x3 into dx3. Therefore, py of y is now given by px of x1 divided by dy by dx at x equal to x1, and px of x2 divided by dy by dx at x equal to x2, and similarly for the third point. In general, if there are n possible roots like this, the probability density function of y is given by the summation over all these roots, where xi's are the roots of the equation g of x equal to y. Okay. Now, you have noticed that we are putting modulus here. It is just to ensure that we add the probabilities. Probabilities need to be positive numbers. So, we wish to ensure that we are adding probabilities. There is no signs associated with probabilities to make that to ensure that we are putting this modulus. So, we can consider in a couple of examples and see what we learn from them. The first example we consider is, we assume that x is a normal random variable with parameter m and sigma, and the function y is defined as exponential of x. Now, x is normal, therefore, the state variable here takes values from minus infinity to plus infinity. Since x lies between minus infinity to plus infinity, based on this rule we can ascertain that y lies between 0 to infinity. So, y is positive, y is non-negative, it lies from 0 to infinity. Now, if we come here, I am plotting y of x versus x here in this graph. This is my exponential function. So, at x equal to 0 it is 1, and as x tends to infinity it goes to infinity, and as x goes to minus infinity it goes to 0. Now, this is my probability density function of normal random variable. This is the mean, and standard parameter or sigma is also reflected in this diagram. We are interested in knowing the probability that y lies between this shaded region y to y plus dy. If y lies between y to y plus dy, x will lie in this shaded region. Therefore, probability of y, density function of y at y is given by px of x divided by the dy by dx series exponential x, which is same as y. So, we substitute into the formula here, and we get the following, this expression for the probability density function of y. The state variable y is appearing here as well as here. This random variable y is known as log normal random variable. The name here originates because if you look at x, which is normal, is actually log y. So, logarithm of y is normally distributed. So, we call it as log normal random variable. This is a typical plot of a log normal random variable. This is a probability density function. Although there is a at y equal to 0, the y is sitting here in the denominator, but log y is in the exponent, and if you apply the L'Hopital's rule, you can show that as y goes to 0, the probability density function goes to 0. So, we start with 0 and it peaks, and this is a probability density function. The associated probability distribution function is here. It is 0 at x equal to 0, and as x tends to infinity it becomes 1. So, this x here is the log normal random variable, a typical plot of that. We will consider another transformation, y equal to ax square. So, first step is we have to invert this relation and find out the roots of this equation. So, x is plus minus square root y by a, and what is dy by dx? It is 2ax. So, here we are plotting the function y equal to ax square here, and the given probability density function of x is shown here, and this is the unknown probability density function of y, and if x takes values from minus infinity to plus infinity, y will take values from 0 to infinity. So, the probability that y lies between y to y plus dy is nothing but the union probability of the union of these two events, namely x lies between x1 to this x1 minus dx1 and x2 to x2 plus dx2. So, you will have to add these two probabilities. If we follow those rules and if we add them up, I get the probability density function of y in terms of probability density function of x, which is given, and this is the requisite probability density function. Now, we consider another example. Let x be a normal random variable with parameters m and sigma, and I define a new random variable u, which is x minus m by sigma. Now, we have to invert this relation. X will be sigma u plus m, that is the root, and what is du by dx? It is 1 by sigma. So, the probability density function of u is given by probability density function of x evaluated at the root divided by the modulus of the slope, and if we do that, we get this function, which is actually another normal random variable whose parameter is 0 and 1. M is 0, sigma is 1. So, what we have done is we have carried out a linear transformation on a Gaussian random variable, and we see that the Gaussian property of the random variable is preserved. U is, you can show that u is non-dimensional. Right now it may not be clear, but as we go along we will be able to show that u is non-dimensional. And one more remark that can be made is that the fact that upon a linear transformation a Gaussian random variable remains Gaussian in this particular example, this is an illustration of a general result that Gaussian quantities are closed under Gaussian operations. Later in this course we will see this operation. What I mean here can be a differential operation or a matrix operation, or in other words, if input to a mechanical system are Gaussian and the mechanical system is linear, the output will also be Gaussian. As an exercise, we could consider another problem where x is again normal with parameter m and sigma, and we define a linear transformation on x, ax plus b, where a and b are deterministic numbers, and we can show that y is again normal with mean am plus b, with parameter am plus b and the second parameter a into sigma. This again is an illustration of the fact that a linear transformation of a Gaussian random variable keeps the random variable Gaussian. Okay. Now, we will ask this question now. Let us consider a random variable x. We will ask the question, what constitutes the complete description of this random variable? We have answered this question. For complete description of x, we need to specify its probability distribution function or its probability density function. Now, as engineers, we are always interested in simplifying descriptions. So, we can ask the question, is probability density function always required? An associated question is probability density function always available? This leads to the question, are simpler descriptions possible for a random variable? That takes us to the next topic, namely moments of a random variable, and that introduces us to what is known as expectation operator. So, let us start with what is meant by mean of a random variable. Let x be a random variable, let it be continuous, and Px of x be the probability density function. By definition, the mean of x is given by this integral, x into Px of x dx. If x is a discrete random variable, where this probability of x equal to xi is specified for I equal to 1 to n, by definition the mean of this random variable x is given by the summation I equal to 1 to n xi p of x equal to xi. The word mean is, we are familiar with what it means. The question that we can ask is this definition of mean of a random variable consistent with what we know as mean or the average? Okay. We claim that eta is a measure of central value of x. If I am asked to specify a single number which is most representative of capital X, I would be tempted to offer eta as a candidate. The question, as I was saying, is this notion consistent with our intuitive notion of a mean? By that what I mean, suppose if you have numbers xi, I equal to 1 to n, x1, x2, x3, xn, and I ask the question, what is the average of x or mean of x? Our intuition would say that you have to add all these numbers and divide it by the number of observations, that is the mean of x. We call it as x bar. Now, this can be rewritten as I equal to 1 to r ni xi, where ni is number of observations which are identical to xi. That means, for example, if you are evaluating a class out of 10 marks and you are giving marks as 0, 1, 2, 3 up to 10, and if there are 100 students, some maybe 5 students may get 8 marks, 11 students may get 7 marks, so on and so forth. So, this ni is the number of xi is 7, means ni is number of students who have got 7 marks, right. So, the average is again given by this. Now, what is ni by n, which is nothing but probability of x equal to xi, okay, by one of our definition of probability. So, this summation thus can be given as xi into probability of x equal to xi. This is perfectly consistent with the definition of mean of a random variable for a discrete random variable, which we just now saw. If this number of distinct observations become very large, this summation can be replaced by an integral, and this again is consistent with the definition of mean of a random variable. Okay, this is eta. So, the definition of mean as a moment of a probability density function is consistent with what we think as the so called arithmetic mean. After considering a measure of central value, the next natural question to ask is to define a measure of dispersion. This leads us to the notion of variance and standard deviation. Again, if x is a continuous random variable with probability density function Px of x, by definition the variance is defined as integral minus infinity to plus infinity x minus eta, where eta is now the mean which we already defined, square of that Px of x dx for a continuous random variable, and an associated definition for a discrete random variable where this integral is replaced by a summation. The positive square root of this variance is known as the standard deviation of capital X. We do not assign any meaning to the negative root, this is by convention. Now, variance of X has the units of square of X, that can be verified, whereas standard deviation has units of X, therefore it is preferred over variance. What we have done here is to find out how does X deviate from its central value and squared it and summed it over minus infinity to plus infinity. We may be tempted to offer an alternate definition for measure of dispersion where instead of squaring and then taking a square root, I can as well consider here a modulus of x minus eta and px of x dx integral minus infinity to plus infinity as a measure of dispersion. This is perfectly valid as a definition, but this is not commonly used because this operation of taking absolute value is not amenable for algebraic manipulations. Say a plus b whole square can be expanded as a square plus b square plus 2ab, whereas modulus of a plus b stays as modulus of a plus b. So, this is one reason why this is not preferred, although this also looks perfectly acceptable as a definition. The generalization of the notion of mean and variance can be seen by defining what is known as an expectation operator. We consider x to be a random variable with a given probability density function px of x and consider the function g of x. We say this quantity as expected value of g of x. One can use two notations to write this. One is to use this angular brackets or use these brackets and put a e outside. This e is expectation operator. This is to be read as expected value of g of x. This also has to be read as expected value of g of x. This by definition is this integral g of x px of x dx from minus infinity to plus infinity. In our lecture, I would prefer to use this notation, this angular brackets. This is the expectation operator that I will follow. Now, let us consider what is let a be a constant. What is the expected value of a constant? What it is? This is integral minus infinity to plus infinity a px of x dx. A is a constant, so we can take that outside and we are left with a into this minus infinity to plus infinity px of x dx. What is this minus infinity to plus infinity px of x dx? It is the probability of the sample space, which is 1. Therefore, this is a. So, the expected value of a is a. Now, if g of x is x, what is the expected value of g of x? It is minus infinity to plus infinity x px of x dx, which is nothing but the mean of the random variable x. Similarly, if I now define g of x as x minus eta whole square, the expected value of g of x in this case will be the variance of x. So, to define mean and variance, we can use the expectation operator, which is more general. The mean and variance can be obtained as special cases of the general expectation of g of x. Now, we can give further meanings to g of x. We can say g of x is x to the power of n. We can call them as nth order raw moments, which is given by x to the power of n px of x dx. We can similarly define nth order central moments, where I consider g of x to be x minus eta to the power of n. So, this is integral minus infinity to plus infinity x minus eta to the power of n px of dx. This we call it as nth order central moment. We define the ratio of the standard deviation to the mean as the coefficient of variation. Okay. Now, let us consider what happens in this definition n equal to 0. So, n equal to 0, x minus eta to the power of 0 is 1, expected value of 1 is 1, therefore, mu naught is 1. What is n equal to 1? This is expected value of x minus eta. This can be, we can consider this specific case of n equal to 1 in some detail. So, this is minus infinity to infinity x minus eta px of x dx. This is nothing but minus infinity to infinity x px of x dx minus eta minus infinity to infinity px of x dx. This is nothing but eta and this is nothing but eta. So, this is eta minus eta equal to 0. So, the first order central moment is 0. The second order central moment is nothing but the variance, so on and so forth. Now, we define the ratio of third order moment to the cube of the standard deviation as skewness, and similarly ratio of mu 4 by sigma to the power of 4 as kurtosis. These are non-dimensional entities. Coefficient of variation, skewness and kurtosis are non-dimensional. Now, let us come to now this moment Mn. M1 is expected value of x, which is eta. M2 is expected value of x square, this, and we call this as mean square value, and the square root of this is known as root mean square value. These are some of the terms that you come across. Let us consider a situation where mean is 0, in which case you can see here Mn will be equal to mu n because eta is 0. So, in that case M2 will be nothing but variance, and therefore, the root mean square in that case is nothing but standard deviation if mean is 0. If mean is not 0, the standard deviation and root mean square value are different. The RMS value and standard deviation are synonymous if and only if mean is 0. Now, we can consider this second order central moment, and if we now expand x square plus eta square minus 2x eta, I can write this as expected value of x square. This is a constant, therefore, expected value of constant is eta square, and expected value of 2x eta is 2 eta expected value of x, and we see that this becomes the variance is nothing but mean square value minus square of the mean. That means sigma square plus eta square is mean square value. Since sigma square is greater than 0, it implies that the mean square value has to be greater than eta square. That is, the second moment M2 must be greater than or equal to the square of the first moment, or in other words, the moments of a random variable are not arbitrary. You cannot arbitrarily assign moments to a random variable, they have to satisfy certain inequalities. Now, finally, we can remark that we can have two random variables which may have the same mean and variance, but this does not mean that the two random variables will have the same probability density function, because their other moments can be different. In discussion of moments, we talk about what is known as a moment generating function, that is defined as expected value of a quantity exponential of Sx. So, that is given by minus infinity to plus infinity exponential of Sx px of x dx. You would see that this is nothing but the Laplace transform of the probability density function. So, we define this function as the moment generating function. How does this word originate? To see that, we can expand exponential Sx in a series 1 plus Sx whole square by 2 factorial etc. Now, the moment generating function is the expected value of this. So, if you carry out the expectation operation on this, the left hand side expected value of the left hand side is the moment generating function and right hand side is 1 plus s into mean of x plus s square by 2 factorial expected value of x square, so on and so forth. Now, if you differentiate this now with respect to s and put s equal to 0, what happens? This is 0, this becomes expected value of x, this is plus 2s into this is 3s square into this, so on and so forth. When I put s equal to 0, all other higher order terms go to 0, therefore, the mean value can be obtained as d psi x by ds at s equal to 0. Similarly, the second derivative at s equal to 0 is the second raw moment m2 in general dn psi x by dsn is x to the power of n. So, because of this property we call this expected value as the moment generating function. Here s is in general a complex number. If we make s to be a pure imaginary number, we get what is known as a characteristic function. So, we define the expected value of I omega x where omega is real and I is square root minus 1. This is exponential I omega x p x of x dx. You will recognize that phi x of omega is a Fourier transform of the probability density function. By expanding e raised to I omega x in a stellar series and differentiating that with respect to omega, one can show that the nth order moment is given by the derivative of the characteristic function in this way at omega equal to 0. Now, by using inverse Fourier transform, if I know the characteristic function, I can evaluate the probability density function also. That would mean a random variable now can be expressed in terms of its characteristic function also, and if you have the characteristic function for a random variable, it also constitutes the complete description of a random variable. So, complete specification of a random variable is through its probability space itself omega bp or through the probability distribution function or the probability density function or the moment generating function or the characteristic function. Alternatively, we can specify mn for all orders. If I know m1, m2, m3, mn, what I could do is I could go back and construct the moment generating function using this relation, using this relation, and then I can use the inverse Laplace or inverse Fourier transform and get the probability density function. So, introduction of moment generating function and characteristic function and moments of a random variable expands our toolkit to model uncertainties. So, in manipulating mathematical models, many times it would be easier to deal with a characteristic function, easier to deal with moments, not always we need to deal with probability density and distribution functions. Now, we will consider one example. For a Bernoulli random variable, let us find out what is its mean and variance. So, for a Bernoulli random variable, there are two possible outcomes, x equal to 0 and x equal to 1. The probability of x equal to 0 is p and x equal to 1 is 1 minus p. So, the expected value of x is xi summed over I equal to 1 to 2, probability of x equal to xi. So, x1 is 0, 0 into probability of getting 0 is p plus x2 is 1 and the associated probability is 1 minus p, therefore, mean of x is 1 minus p. Similarly, the mean square value is xi square, probability of x equal to xi running from 1 to 2. So, here again 0 square into p plus 1 square into 1 minus p, which is 1 minus p. Now, what is variance? It is mean square value minus square of the mean. So, it is 1 minus p minus 1 minus p whole square and I get p into 1 minus p. So, square root of this is the standard deviation. The characteristic function phi x of omega is expected value of exponential of I omega x. So, exp I omega of 0 into p plus exp into I omega into 1 minus p, this is p plus 1 minus p exponential I omega. And from this I can show that all Mn is 1 minus p. See, you have noticed now that this is nothing but M1 which is 1 minus p, this is 1 minus p, and this is M2, this is 1 M1, this is M2 which is again 1 minus p. Using this characteristic function you can show that all Mn are 1 minus p for this random variable. So, we will close this lecture at this point, we will continue with this in the next lecture.